Good morning, everyone. I'm Pooja Dobhal, Marketing Coordinator at Sengers, and the moderator for today's webinar on the Introduction to Seismic Cone Penetration Testing. Today's session will cover the fundamental of seismic cone penetration testing, its component, working principle, and basic interpretations. Whether you are practicing geotechnical engineer and a base, or a project consultant or a curious learner, we hope this session adds value to your work and understanding. It's my pleasure to introduce our speaker, Dr. Abhishek Shakleshwar, geotechnical engineer at Sengers. He has completed his integrated BEME in civil engineering from Andhra University and earned his PhD in geotechnical engineering from Purdue University, USA in 2024. He has worked extensively on cone penetration testing, foundation systems, MSC walls, and bridge abutments, and has authored over 40 technical papers in national and international forums. He is also a recipient of prestigious honors, including the ADSC One Case Memorial Scholarship, DFI Global Roche Lincoln Scholarship, and Gerald and Beryl Leonard's Fellowship from Purdue. With that, I now invite Dr. Abhishek to take us through the presentation. Over to you, sir.
Thank you, Pooja. Is my presentation on the screen?
Yes, sir. Yes.
So good morning, everyone. And today we'll talk about the seismic cone penetration test and what it's about. So the outline of my presentation is as follows. So first, a brief glance at Sengers, then an overview of the CPTu, then the seismic cone penetration test or the seismic CPTu, a brief introduction and background, the test equipment and procedure, and then how do we analyze the data and interpret the data. Then we look at some sample SCPTu results, and we'll compare the SCPTu with other methods for seismic testing. Finally, concluding with best practices and Q&A. So a brief introduction about Sengers. So we are a top geotechnical consultancy in the country, founded in 1990 by IIT Delhi alumni. We have a permanent staff of over 150, and we've published over 85 technical papers, more than 250 projects annually, and a total number of projects of more than 6,900 in the Indian subcontinent, with over 1,500 satisfied customers. We offer 360-degree solutions, starting from geotechnical investigation over to geotechnical consultancy, including analysis and design, and finally, foundation quality analysis, quality assurance, and quality control. And we have a huge pan-India presence with over 7,000 projects completed in the past 35 years, and we have the largest subsurface exploration data bank in the entire country. Now let's look at the CPTu first, which is an electric cone penetration test with pore pressure measurement. So the CPTu, or the piezo cone penetration test, it basically involves pushing a cone hydraulically into the ground at a standard rate of 2 centimeters per second. And as the cone is pushed into the ground, we measure the resistance to penetration, which is the cone resistance, the skin friction or the shaft resistance, which is the sleeve friction, along with a sensor that can measure the pore pressures during penetration. Now, here on the right-hand side, we can see plots of tip resistance, sleeve friction, and pore pressure. And these plots give us a continuous profile of soil resistance with depth. And it gives us an indication of not only the soil type, but also the state of the soil and the shear strength of the soil. There are various codes of practice for the piezo cone CPTu. For example, we have the ASTM D5778 and also a draft Indian standard IS 4968 Part 4, which is currently under review and is expected to be finalized soon. Now, the pushing equipment involves either a tractor or a crawler mounted CPT rig or CPT trucks. And when we push the cone, we basically connect a series of rods, 1 meter long rods, as we push the cone into the ground. Here on the bottom, we can see more pictures of the penetrometer and the CPT probe itself. So the probe contains various sensors such as load cells or pore pressure transducers that allow us to measure these various quantities. Now, in addition to the parameters that I described previously, the CPTu also allows us to estimate the hydrostatic pressure from which we can calculate the depth of the groundwater table. Now, what the pore pressure recorded during the cone's movement through the soil represents is the dynamic pressure rather than the hydrostatic pressure. So usually when we perform a CPTu pore pressure dissipation test, we wait for the excess pore pressures to dissipate. And then once the pore pressure has stabilized, we can then calculate the hydrostatic pressure from that and estimate the groundwater table depth. We can also estimate the consolidation and flow characteristics of the soil from CPTu dissipation test results. Now, the CPT has many advantages. Basically, it's cheaper, faster, and better compared to the traditional method of site investigation, which is doing boreholes. So the first advantage of the CPT is that it's fast. The cone is pushed into the ground at 2 centimeters per second or 1.2 meters per minute, or we can complete a CPT sounding of 30 meters in just half an hour. We can get continuous or near continuous data from the CPT. It's accurate. The data quality is much better. It's enhanced, and we can get simpler and reliable electrical measurements of these various parameters. And the data is automatically recorded to the field computer on site. The CPT is versatile, so we can estimate a wide spectrum of CPT-based geotechnical parameters for foundation analysis. CPTs can be performed to depths exceeding 100 meters in soft soils. The CPT is reliable, so what that means is the data is independent or irrespective of the person or the contractor, the operator, and the equipment used to perform the test. It's also possible to collect discrete soil samples using CPT samplers. The CPT is modular, which means we can combine various sensors to get other quantities of interest, including shear wave velocity, which we'll talk about today, along with other parameters like inclination, thermal resistivity, and so on. The CPT is safe in comparison to the SPT, so we don't have any hammers or rotating parts involved here. It's clean, so there's no drilling mud or muck. And finally, the CPT is cost effective, and the testing cost is not much more than the cost of conventional boreholes. However, the CPT does have some limitations that we need to keep in mind. For example, it involves initial capital investment as compared to conventional drilling rigs. It requires skilled operators. The penetration of the cone can be restricted in gravel, cemented soil layers, and the CPT cannot be used in harder formations like rocky formations or cobbles or bouldery type of formations. It may still take some time to build experience and confidence in India, but the CPT is gradually being implemented, I would say, in site investigations. Despite these limitations, I think that the advantages of the CPT technology far outweigh these limitations. This slide basically shows how it's possible to collect soil samples using a CPT sampler. So basically, the CPT sampler is a push-in type of sampling system that's compatible with CPT rigs. So when the cone reaches the desired depth, there is a piston that gets retracted and locked, and then the piston is pushed into the ground to obtain a soil sample at that depth. And then these samples can be returned back to the laboratory for performing various tests in the lab. Now let's look at seismic testing and what it's about. So in seismic testing, basically we generate different waves. So we have two main types of waves, which are compression waves and shear waves. How do we generate these waves? The waves are generated by striking a shear beam that's placed on the ground surface. So when we strike the beam vertically, we generate compression waves or P waves. And when we strike the beam horizontally, we generate shear waves or S waves. Now, these compression waves or P waves have particle motion that's parallel to the direction of wave travel, and it's generated using a vertical impact on the source. Whereas shear waves or S waves have particle motion that's perpendicular to the direction of wave travel, and they are generated by striking the beam horizontally. Now, the next slide shows an illustration of how shear waves and compression waves are generated, their propagation direction relative to the particle motion. There are various in situ seismic tests that can be used in geotechnical investigations. So we can classify them into two main categories: invasive techniques or non-invasive techniques. The seismic cone test, which will be the focus today, comes under the category of invasive techniques because we are pushing the cone into the ground. Similarly, we have other tests like the seismic flat dilatometer test, the downhole seismic test, crosshole seismic test, and suspension logging, all of which fall under the category of invasive techniques. On the other hand, non-invasive techniques do not involve pushing anything into the ground. So here we have tests like MASW or SASW, seismic reflection surveys, passive seismic surface waves, continuous surface waves, and reflection microsize. So there are a whole bunch of seismic tests that's available for us, but today we'll focus on the seismic cone test. Before we get to that, let's try to understand why do we need these seismic tests in the first place. So the first reason why we need seismic tests is to determine the seismic site class using appropriate building code, for example, as specified in IS 1893 Part 1. Seismic tests are also useful for liquefaction analysis, for example, calculating the factor of safety against liquefaction and liquefaction-induced ground deformations. Seismic tests are also useful in the static analysis of foundations, particularly in the calculation of immediate settlements through the Young's modulus E. Also in dynamic analysis of foundations, particularly in the estimation of dynamic soil parameters like the dynamic Young's modulus, dynamic shear modulus, and Poisson ratio, which are useful for machine foundation design. And seismic tests are also useful for identification of cemented soils or soils with significant aging or microstructure, as we'll see in the following slides. This is an excerpt from the draft Indian Standard Code, IS 1893 Part 1, which is under wide circulation, which specifies that VS30, which is the average shear wave velocity over the top 30 meters of the ground, is mandatory for site class assessment. So here we can see, depending on the weighted average shear wave velocity, the sites are classified in various categories ranging from A to E, depending on the value of the shear wave velocity. The shear wave velocity is also useful for liquefaction susceptibility assessment using charts of this form. And for static and dynamic modulus for foundation design. So from the shear wave velocity, it's possible to get the dynamic shear modulus or the small strain shear modulus G. And from G max, using the theory of elasticity, we get to the small strain Young's modulus. And then we need to apply a certain degradation on the small strain Young's modulus to get the E value that is representative of strain levels that are applicable in settlement analysis of foundations. In terms of identification of cemented soils, now the cone resistance QT is actually a measure of the large strain soil strength or resistance. Now, from a seismic piezo cone test, we get the shear wave velocity, which is actually a measure of the small strain soil stiffness, G naught. So by combining the measured shear wave velocity with regular CPT data, it's possible for us to identify soils that have significant microstructure, aging, and cementation. So this is a chart from Robertson 2016, where we have a normalized rigidity index, Kg star, that can be used to estimate the magnitude of microstructure. So this normalized rigidity index is basically a function of G naught, the small strain shear modulus, Q net, which is the net cone resistance, and capital QTN, which is the normalized cone resistance. So basically, if this parameter Kg star is less than 330, it means that soils are likely young and uncemented with little or no microstructure. And if it's more than 330, it means that we likely have significant microstructure. We need to note here that the traditional CPT-based correlations that we typically use in foundation analysis and design are actually applicable to ideal soils or soils that are unstructured and uncemented. So when we do encounter sites with significant aging or cemented soils, we may need to modify these correlations or apply local experience on a case-by-case basis. Now let's look at the seismic cone penetration test, the SCPTu. So how does the SCPTu work and why does it excel? So basically, the seismic CPTu is nothing but your regular CPTu, but we attach a seismic module to the CPT probe, and we have a shear wave source at the ground surface. Now, the seismic module consists of two geophones, a top geophone and a bottom geophone that is capable of recording the arrival of shear waves or compression waves. Now, to generate these waves, we need a source that is typically a shear beam that is at the ground surface. So when the beam is striked, we generate vertically propagating and horizontally polarized downhole shear waves that are picked up by the geophones. Now, depending on the arrival time of the waves and the distance from the source to the geophones, we then calculate the shear wave velocity using this equation here. Now, from the SCPTu, we not only get QC, Fs, and U2, but also the shear wave velocity, so covering strength, stratigraphy, and stiffness. It allows high resolution profiling, so continuous measurements can detect subtle changes in stratigraphy that may be missed by conventional boreholes. As I mentioned earlier, VS underpins seismic site classification, foundation design, and liquefaction assessment. And the benefit of the SCPTu is cost and time efficiency. So by merging the regular CPTu with seismic testing, it allows faster data collection, fewer mobilization, and more robust results. So the ASTM standards are listed here for the CPTu and the downhole seismic test. And this slide illustrates further what I mentioned previously. The shear wave arrivals are usually taken at 1 meter rod intervals. So whenever we are performing the CPT, whenever we have to apply the next 1 meter rod to push the cone, it allows us to get measurements of shear wave velocity at those depths at every 1 meter rod intervals. On the right hand side, we can see a plot of the shear wave velocity with depth, and VS provides a direct measurement of the soil stiffness. And here we can see other features, so the cone resistance, sleeve friction, pore pressure, and the geophone, which is part of the seismic module that is connected to the CPT probe. Now, there are various sources for us to be able to generate these waves. One such source are called pendulum hammers. So basically, these pendulum type of hammers enable the pulling and releasing of a rope instead of manually lifting the hammer and hitting the shear beam every time. So basically, it's an automatic process instead of having to lift the hammer manually and then strike the beam ourselves. And in these photographs, we can see various setups of the pendulum hammer system. So every time the hammer is lifted, and when it strikes the beam, it generates these shear waves. The top geophone and the bottom geophone record two different waves. So the blue color corresponds to the top geophone and the red color to the bottom geophone. And as the waves are recorded, we are able to get these seismograms, as we see here. So the blue wave actually arrives faster than the red wave, so that's why the red wave has a delay compared to the blue wave. And the way shear wave velocity is calculated is by taking the difference in the distances divided by the distance in the arrival times. Once we get the shear wave velocity, we get the small strain shear modulus using this equation. Here on the right-hand side, we can see various seismograms collected at different depths. So the shear wave source plays a crucial role for the quality of the seismograms, the efficiency of the VS automatic interpretation, accuracy and repeatability of VS data, as well as the maximum depth up to which we can perform the seismic CPT, because we need to be able to generate a sufficient wave that can travel up to the depth where we have the geophone. Now, when we collect these measurements, we need to know whether is the data of a good quality or it's not of a good quality. So the way we can do that is first by looking at the plot of the seismogram, it must clearly show the following sections. So first, there should be an initial silence of low amplitude before the arrival of the S wave. What that means is before your main S wave is actually picked up by the geophone, you need to be able to see an initial silence in the seismogram. Then second, the main S wave, which is of a high amplitude, is recorded by the sensors, as we see over here. And then finally, the seismogram has a tail of medium to low amplitude of reflections and refractions, which is what we see here on the right. So these are the three main features that you need to look for in a seismogram to know that your data is of good quality. And the main S wave should exhibit a consistent delay between the waveforms. What that means is if you compare the blue wave and the red wave, the delay between the two waves should be consistent across the main shear wave. So that tells you that the data is of good quality. And then another way to check for the repeatability of your seismic measurements is through the coefficient of variation. So this is basically the ratio of your standard deviation to your mean. And if the coefficient of variation is less than 1%, it means that you have excellent repeatability in your data. However, if your coefficient of variation is more than 10%, then it means your data is not repeatable or is of poor repeatability. So when we process the seismogram, what we see here on the top are the original non-filtered signals. What we do next is we apply a certain smoothing on the original non-filtered signal to then get a smoother filtered signal that we see here in the middle. And then the program or the software automatically rephases the two signals, meaning it attempts to adjust the blue wave and the red wave to accurately calculate what is the delay between the two waves. And then by knowing the delay between the waves, we then get the shear wave velocity from that. The plot that you see here on the bottom is actually within a shear wave velocity ranging from 50 milliseconds all the way up to 75 milliseconds. So this is actually an expanded plot of the gray box that you see over here. So this is just simply expanded on the bottom. And here we can see the test depth, which was 10.5 meters at which this test was performed. The shear wave velocity at this depth as we can see here, is 190 meters per second, and the delay between the two waves is 2.6 milliseconds. So the program or the software applies a cross-correlation algorithm, and it attempts to shift the red signal back towards the blue signal until the best match or superimposition is obtained between the two, from which it automatically reports the delta t, which is the delay between the two waves. So these are some examples of data analysis and interpretation. These are examples of smooth shear waves in a clay soil profile. So we can see the initial silence, then the main S wave, followed by the tail of the wave, and note the consistent delay between the blue and the red wave across the main shear wave. Then this is how the plot looks like after the two waves are rephased to get the wave delay. And here we can see the test was performed at a depth of 20 meters, where the shear wave velocity was 114 meters per second, and the coefficient of variation was less than 1%, indicating excellent repeatability. However, sometimes in sandy soil profiles, we may obtain less smooth shear waves. However, what's important to note is that the shear wave velocity is actually related to the delay between the waves and not to the shape of the waves. So it's important to check that the delay between the waves is consistent across the wave, not necessarily the shape of the wave. Now let's look at some sample seismic CPTu results that we performed in Kutch, Gujarat. So these are some example seismograms from SCPTu 105. What you see on the left-hand side are seismograms from 0 to 10 meter depth at 1 meter depth intervals. So meaning that the plot on the top is at a depth of 1 meter, going all the way down up to a depth of 10 meters. We can see the actual raw data or the recorded signals on the left, and then the rephased signals on the right. Then here, similarly, we see seismograms continuing from 11 meter depth down to 20 meter depth, similarly in 1 meter depth intervals. And we can note the excellent quality of the seismograms. So by processing the SCPTu data, we can then prepare plots of shear wave velocity with depth, along with the small strain shear modulus or the dynamic shear modulus, G0, with depth. So here we did 5 seismic CPTUs at this site, and we can see some similarity between certain seismic CPTUs, indicating similar stratigraphy in those areas compared to some variability in stratigraphy depending on the profile of the shear wave velocity here. Now, when we present our data, usually we present plots of cone resistance, then we have sleeve friction, friction ratio, which is nothing but the sleeve friction divided by your cone resistance. Then we have plots of pore pressure, and then the soil behavior type. So these are standard results that we get with the CPTu, but the benefit of the seismic CPTu is that we can also get measurements of shear wave velocity as well as the small strain shear modulus. So the data points that we see here are actually measured or measurements, and the solid black line is the interpreted or the correlated shear wave velocity from CPT data. And we can note the excellent match between the interpreted shear wave velocity as well as the measured shear wave velocity. Now, as I mentioned previously, we can also perform CPTu dissipation tests, which we also did at this site, and we can note the good match between the measured permeability determined from dissipation test results versus the interpreted permeability from CPT correlations. Other parameters that we can get from CPT results are the interpreted N60 value, unit weight, undrained shear strength, and friction angle. Now, from the seismic CPTu, from the shear wave velocity, we can perform liquefaction susceptibility assessment. So here on the left, what you see is the raw shear wave velocity data. Then in the middle, we have plots of cyclic stress ratio and cyclic resistance ratio. Then the factor of safety against liquefaction. So here we can see, for example, liquefaction is likely to occur from 0 to about 1.5 meter depth, and again from about 4.5 meter to about 6.5 meter depth. And these are actually layers where we have silty sand, sandy silt type of profiles, which are susceptible to liquefaction. Note the water table is near the ground surface, and other layers are mostly clay or silty clay type of material, which are not likely to liquefy. Now, the benefit of doing a shear wave velocity liquefaction analysis is the liquefaction potential index, which quantifies the risk of liquefaction. So here, for example, when the index is approximately about 17 or so, it indicates that the risk of liquefaction is high for this site. So provides a quantitative measure. There's another histogram showing liquefaction potential index for each of the 5 seismic CPTUs that we did at this site, along with the classification or the risk of liquefaction, depending on whether it's low, high, or very high risk. Now, as I mentioned previously, one of the advantages of the seismic CPTU is the identification of cemented soils. So these are some example results from the same site in Gujarat. So here we can see that based on the measured, based on the data points, they more or less plot near the value of 330 for that normalized rigidity index, indicating some level of cementation or microstructure at this site. However, note for SCPTu 101, most of the data points actually plot above the line, which means the rigidity index is more than 330, indicating significant cementation in this area of the site. Now let's look at the seismic CPTU versus other methods of seismic testing. But before that, just want to briefly recap the benefits of the CPTU. So we can get enhanced ground characterization. So plots of cone resistance, sleeve friction, pore pressure, and shear wave velocity. Note that wherever we have very soft clay, we have very low cone resistance, high pore pressures, exceeding the hydrostatic pore pressure, which is the light blue line that you see here, and low shear wave velocities around 100 meters per second. Now, wherever we have, let's say, dense sand or medium dense sand, we can see an increase in cone resistance. The pore pressures come back to the hydrostatic pressure in the sand layers, and then we can see an increase in shear wave velocity going up to about 300 meters per second in the sand layers. Now, the SCPTU is versatile, meaning that we can get many soil parameters of interest in design. So for example, from pore pressure dissipation, we can get the coefficient of permeability and the coefficient of consolidation of the soil. We can also get the groundwater table. From the cone resistance and sleeve friction, we can classify the soil according to these soil behavior type charts. We can also estimate OCR, over consolidation ratio, pre-consolidation stress, along with the small strain shear modulus, Gmax, if we also perform seismic cone penetration tests. And finally, the SCPTU is highly repeatable. And so this is an example where 3 different measurements of shear wave velocity were taken at the same depth of 30 meters. And we can note the values are very close to each other. So 216, 217, and 217 meters per second. So excellent repeatability in the data. Now this slide compares the SCPTU with other methods. So if we look at the seismic dilatometer test, it also measures the shear wave velocity, but the difference is that it uses a dilatometer blade instead of a cone in the case of the seismic CPTU. So here, that's indicated by this figure here on the bottom right. The SCPTU actually can penetrate deeper and includes more robust cone-based correlations than the seismic dilatometer test. In the case of the downhole seismic test or the crosshole seismic test, these tests actually involve or require pre-drilled cased boreholes, which can increase the time and cost. And because boreholes are involved, it's important to make sure that the boreholes are vertical. And so doing a borehole deviation survey is needed for the crosshole seismic test, because if your boreholes are not vertical, your measurement of your shear wave velocity will not be accurate. The SCPTu approximates downhole accuracy in a single push. Coming to seismic waves such as MASW, SASW, which you see over here, these are non-invasive and are effective for identifying lateral soil variability in large sites. So they can cover a large extent of soil in the lateral direction. However, these tests are sensitive to ambient noise and sometimes have low vertical resolution in stratified soils. All these are in situ tests. Now, in addition to in situ tests, it is possible to also collect uh, undisturbed samples, bring them to the laboratory, and do laboratory testing on them, such as resonant column, torsional shear, or bender element type of tests to get the shear wave velocity and the small strain shear modulus. But these are typically performed in research projects, not so much in our routine site investigations that we do in the industry. This slide compares the data collected from the seismic CPTu with data from crosshole seismic test. So here in the plot, what you see is shear wave velocity with depth. The solid line is the interpreted shear wave velocity from CPT correlation. The red line is the measured shear wave velocity from a seismic cone penetration test. And the green line is the measured shear wave velocity from a crosshole seismic test. So we can see that the results are in good agreement with each other. However, the benefit of the seismic CPTu is we can save 40% in the cost and almost 99% saving in time compared to the crosshole seismic test. In addition, we get all these parameters: cone resistance, sleeve friction, and pore pressure with the SCPTu. The SCPTu covers strength, stratigraphy, and stiffness all in one test, which CHST cannot. So CHST lacks strength and the stratigraphy data, and SCPTu enables faster data collection, fewer mobilization, and more robust insights. On the right-hand side, we're comparing the SCPTu with the standard penetration test. So what we have is the modulus of elasticity E plotted against depth. So the black solid line is the E value determined from SPT correlation, and the red line is the E value from the seismic CPTu. So we can see that the modulus from the seismic CPTu is almost 2.5 times greater than the E value from the SPTN. So indicating higher stiffness, which results in higher net allowable bearing pressure, resulting in smaller foundation sizes, so faster construction and reduced overall cost. Here on this slide, we can see the benefit of the seismic CPTu. So basically, the main takeaway from this is that it's cheaper, faster, and better compared to other tests such as MASW, SASW, DHST, and CHST in profiling VS to a depth of 30 meters. In terms of best practices, it's always good to combine and cross-check. What that means is it's always good to pair your SCPTu with other standard tests, such as the SPT pressure meter test or a crosshole seismic test, to obtain a multidimensional site model. The more information that you can have about your soil profile and the ground, the better informed decisions that you can make and the better analysis that you can do for your foundations. It's important to consider the type of soil that you have at your site. For example, if you know or you expect that the soil type is likely to be dense gravel or cemented type of soil layers, this may limit the cone penetration. So you need to plan accordingly for such type of sites where it's difficult to push the cone into the ground. when we have seismic zones and where earthquake design is mandatory, the SCPTU's direct shear wave velocity measurement is invaluable in such sites. So we believe that the seismic CPTu is the future of good geotechnical investigation. And then these are some photographs of Senja's team carrying out seismic CPTs at a project site in Delhi NCR. Thank you for your time, and I would be happy to take questions.
Thank you, sir, for the insightful presentation. Now, let's move on to the QA session. I request everyone to please continue posting your questions in the comment section and we'll address them one by one. So, our first question is from the Manjot. What are the typical application of seismic CPTU in infrastructure or foundation design projects?
So application of seismic CPTu in infrastructure or foundation design projects. So as I mentioned earlier, um, if your infrastructure or your foundation project is in a highly seismic zone where liquefaction analysis is mandatory or is required, so the seismic CPTu can allow you to get the shear wave velocity from which you can do a liquefaction analysis. The other application is in getting the modulus value from the seismic CPTu. So if you know the modulus or the ground stiffness, you can input that into equations that allow you to calculate foundation settlements or in dynamic analysis of machine foundations, for example. So this is how you can apply your seismic CPTu in foundation design projects.
Thank you, sir. Next question is from Steen Nivasi. Is it the minimum standard to use two geophones in the bottom sensors?
I think it's always good to at least have two geophones in your seismic module because that gives you a true interval, as they say, of the shear wave velocity. Because in order to calculate the shear wave velocity, you have to take the difference between uh, the wave distances and then the wave arrival times. So by having two geophones, it can give you more accurate assessments of the shear wave velocity compared to just having one geophone.
Next question is from Iqbal Hamza. How reliable are the results compared to other geotechnical testing methods, as no physical samples for lab testing?
So as we have seen in some of the slides today, the seismic CPTU results, especially the shear wave velocity, is comparable to the cross-hole seismic test, but there are some cases where there may be some differences between the two tests. However, the general consensus is that the seismic cone penetration test is much better compared to other in situ tests for shear wave velocity. In terms of physical samples for lab testing, so the new advancements with the CPT is the CPT sampler that can actually allow you to collect soil samples at discrete depths. So it is possible to modify the equipment for your cone penetration test to be able to retrieve these soil samples for lab testing.
Next question is again from Devasis. How many waves should we produce at the surface to get good quality signal?
Usually, it's good to at least have, I would say, 4 to 5 measurements at one depth, because then that will give you a good amount of confidence in the repeatability of your data, and then you can then calculate the coefficient of variation, as we saw earlier, using these, let's say, 4 to 5 measurements at the same depth. And so you can then be confident that your data is repeatable and that your shear wave velocity will be accurate.
Next question is from Neha. In what types of soil condition is seismic CPTU most effective or beneficial?
It is most effective or beneficial in any type of soil condition in which that you can uh, push the cone. So the first requirement is that you need to be able to push the cone into the ground. So if your ground has dense gravel layers, rocky formation, bouldery type of material, there it may limit the the ability to perform either cone penetration tests or seismic cone penetration tests. So in such type of soil profiles, you would have to resort to other methods of in situ seismic testing. Most effective, I would say, in soil profiles where in soil profiles that are susceptible to liquefaction, particularly if you have silty sands, sandy silt type of profiles below the groundwater table in a high seismic zone, then seismic CPTu is very, very advantageous there.
Thank you, sir. Next question is from Megha. How reliable is the data from SCPTu when compared to geophysical methods like MASW or downhole testing?
SCPTu compared to downhole testing, I would say the SCPTu is uh, more reliable, basically because in the downhole testing, you have to first make a borehole, ensure that your borehole is vertical, and then you collect your shear wave velocity at different depth intervals. The benefit of the seismic CPTU is not only you get shear wave velocity, but additional parameters that can be used in design. Comparing seismic CPTU and MASW in terms of reliability of the data, I am not fully sure on that question, so I'll have to revert back to you after the presentation.
Next question is from Karthikeyan. How the number of investigation for a project is determined and also depth.
That is a good question. Actually, we do have an Indian standard code. I forget the number, but in the IS code, we have guidelines for uh, the number of boreholes that need to be drilled for each type of project and the depth up to which we need to perform the site investigation. So generally, as a thumb rule, if you have a building type of project, it's IS 1892. Usually one borehole or a CPT sounding in the middle of the building and then one each at the four corners of the building. There are other guidelines in IS 1892 for other types of infrastructure projects or other types of constructions. The depth of the investigation also depends on your pressure bulb or the zone. So first it depends where the depth of your foundation and then the pressure bulb below the foundation. So you need to investigate at least up to that depth to cover the soil below the foundation.
Kartike also asked, any preliminary information about subsurface condition is required before starting investigation?
Usually, if we do have some information about the subsurface conditions in that region, for example, if previous investigations have been done in past projects in the vicinity of your current project, that could give you some indication of the anticipated stratigraphy at the site, which can then allow you to plan your site investigation better. But sometimes, if we don't have any information about the site, usually we would have to first plan a certain amount of boreholes or a certain amount of CPT soundings to then get preliminary information from which we can then refine or customize future investigations for that site.
Saurabh sir has answered Kartike's question. Thank you, sir, for answering.
Yeah.
Next question is from Ritik. What software or tools are commonly used for interpreting SCPTU data?
There are various softwares or tools that are available in the market. One of them is the SDMT Pro that I think is most commonly used all over the world, but there may be other types of softwares and tools as well.
Next question is from Mohan. How does SCPTu support site classification for seismic design as per IS or international codes?
So as per the IS code, uh, by getting the shear wave velocity from the seismic TPTu, so the weighted average shear wave velocity over the top 30 meters of your soil profile, there is guidelines in the IS code that if your shear wave velocity is within a certain range, then your site is classified as A, B, C, D, or E. That again then leads to other, how do I say, procedures as specified in the IS code, but basically through the shear wave velocity.
Thank you, sir, for answering the question. Thank you, Hamza. Thank you, sir. Next question is from Abhishek. What kind of calibration or quality control checks are recommended before relying on SCPT data for design?
So you have to make sure, obviously, that your seismic sensors are properly calibrated. So that requires skilled operators and people who know how to do those things. So it's important to have skilled people for that. In terms of quality control checks for your seismic data, so as we saw in the presentation, your seismograms are what's most critical. So as you're collecting the seismic data, and when you look at the seismograms, it's important to ensure three main things: the initial silence in your shear wave, then the main shear wave of high amplitude, followed by the tail of the wave. And your main shear wave should have a consistent delay between the top geophone and the bottom geophone. So by inspection of these seismograms, it can tell you whether the data is of a good quality or not. And then when you collect multiple seismic measurements at the same depth, you can then calculate the coefficient of variation to check if whether your data is repeatable at that depth or not. So these are the ways you can ensure the quality of your data.
Thank you, sir. Last question we are taking today is from Subinoy Vishwas. If I have 5,000 square meter of land, then how many tests is required? He has also continued his question. How can I understand that how many CPT tests I have to do for a specific area? First question.
So, in terms of not only the area of your land, I think we also have to keep in mind what is the type of structure that is going to be built in that area. So, for example, if it's high-rise towers or if it's solar power plants or wind turbines type of foundations, so it varies from structure to structure. You would have to plan the number of tests according to that. So, depending on where your structure is located, the importance of the structure, and the depth to which you need to do the investigation based on the type of structure. So, I don't think I have a single answer to your question, but it has to be evaluated on a case by case basis.
Uh, Thank you, sir, for answering the question. That's all for today. Thank you, sir. Thank you to all our attendees for joining us for today's session. Before we wrap up, mark your calendar for our next webinar on geotechnical investigation in challenging soil conditions, scheduled for 20th September 2025. Stay tuned for more details and feel free to connect with us on social media or via mail for any further queries. Once again, thank you, sir. Thank you, all of you, for joining us. We look forward to seeing you at our future events. Have a wonderful day.
Thank you, everyone. Thank you.